Bueno, yo creo que vamos a empezar con las presentaciones, así vamos quitándonos este tiempo encima. Bueno, yo voy a hacer la primera, que es presentaros a todos a Emmanuel Monpó, ¿vale? Que va a ser un colaborador, vamos, organizador también del seminario, así que lo veréis bastante por aquí. Y bueno, le voy a dejar el micrófono para que él se presente y presente también la conferencia de hoy. Nada.
Hola, buenas a todos. Bueno, yo voy a presentarlo a él directamente. Vale, bienvenidos a otra sesión del Seminario Junior del Instituto Gregorio Millán Barbani, instituto que financia el catering que va a haber después del seminario y, como saben, también van a haber pizzas para las cuales aceptan donativos de €1 o lo que puedan. Bueno, hoy la charla la da William GRACIAS, que es estudiante de doctorado en el Departamento de Física de la Carlos III y trabaja sobre reacciones de fusión. Y nos va a hablar sobre cómo convertirse en una estrella sin morir en el intento. Bueno, muchas gracias, William.
Gracias. Buenos días. Mi nombre, como ya sabéis, es William GRACIAS y voy a hablar en inglés porque no controlo muy bien español, cosas técnicas. Pues pido disculpas si está alguien que no domina inglés, pero espero que al final de la charla vais a entender todo y me vais a hacer preguntas. Okay, so, the title of today's talk is Making a Star in a Bottle While Trying Not to Destroy Earth. As you know, stars don't exist on Earth, they exist in our universe. And we know that from childhood physics that stars are extremely massive and the gravitational pull could destroy anything that's close by. So just the idea of trying to build a star or make a star on Earth is quite science fiction-like. But what I'll show you in the following slides and probably convince you is that it's possible. Well, the first step is we could try and steal a star, but like we said earlier, it's maybe not possible. So we could dream about it, but we could maybe try and make our own star, yeah? Trying to make a star does seem difficult, but the process, if you think about it and try and break it down into small bits, is quite easy. So for example, there are these 4 reactions that are basic examples of what happens in a star. The first one is a combination of two deuterium atoms, which give us helium and a neutron and some amount of energy released. Now, there are several others that can be used to create a reaction that occurs in a star. And these are called fusion reactions because you have 2 very lightweight, small atoms that combine together after you've supplied them with sufficient amount of energy to overcome the nuclear forces and combine them to give us a new, larger, or rather heavier element. In the first reaction case, it's helium and a neutron and some energy. Now, this differs from what we conventionally know as fission, and this is what's shown here in these 2 diagrams. As you know, the fusion is the fusing or the combining of 2 atoms, and fission is the splitting of an atom. Now, the difference between the 2 is that in fission, it's an extremely heavy element, and so when it splits into 2 lighter elements, but which are still quite heavy. And in this case, you have 2 extremely light elements. I mean, you have isotopes of hydrogen, so this is the first element in the periodic table, so this is extremely light. And these are combining to give us something slightly bigger. Yeah? So now, if you think about it, the amount of energy released in the 2 reactions is not the same, but if you look at the amount of energy released by both of them, divided by the number of nucleons you have in each reaction, so for example, nucleons are the total number of neutrons and protons in an atom. By the very fact that fission entails using heavy elements and gives us byproducts that are extremely heavy too, the amount of energy released per nucleon in fission is less, whereas in fusion it's more. And so just to have an idea of how this works, if you take 1 kilo of fusion elements and produce energy, then the amount of energy produced by that would be far more than 1 kilo of fission elements, just to give you an idea. Okay. So fusion is desirable in that sense because you need very little fuel to generate energy, and this is what we're going to try and see how we can make in our own homes. So that's what I said here. The amount of energy released per nucleon is higher in fusion. And another point to keep in mind is that there are no long-lived radioactive byproducts, except for this reaction here, which produces tritium. Tritium has a half-life of about 12 years. But in this case, you have cesium in fission, which produces cesium. Sorry, this is cesium here. Cesium has a half-life of about 30 years. So the amount of investment and time needed to store these byproducts and then eventually decay them and then remove them and so that they're safe is very long in fission. In the case of fusion, it's not. And there's another reason why it's not, is because the amount of tritium produced is very little. And usually in fusion reactor concepts, the tritium is envisaged to be used again in the next cycle. So it's not something that you would throw away easily or need to stock somewhere. Yeah. So we don't have this problem with fusion where you would need to stock large quantities of wastes, radioactive wastes. And of course, we use isotopes of hydrogen, which is easily recoverable from water. And we know that 70% of the Earth is water. So there's an abundance of fuel. There are lots of things going on here for fusion, whereas the case for fission is slightly disadvantaged. Well, let's see how we can use these reactions. Now, it's not so evident why you can't do this at home because, well, maybe it is. If you look at a star, the temperature and the pressures involved, they are extreme. So you can't think of doing that in your backyard or in your kitchen. You have millions of degrees of Kelvin of temperature that's needed to kickstart this reaction. And the pressures that are achieved are also extremely high. So we would need a sort of a vessel or a chamber to keep these products isolated from the rest of us so that we don't die, and kickstart the reaction by supplying this extreme amount of heat and pressure. Now, once we've started the reaction, we would also need to keep it going on for a long enough time so that the star or the little glowing reaction that you have in the vessel continues to generate energy, because there's no point in just having a small explosion and watching some fireworks. We'd like this to go on and generate some energy for us. So the trick to doing that is to provide sufficient energy at a sufficient time scale and also recover far more energy from this. So we need to have more energy coming out than what we're putting in. And this is what we call as the yield or the gain factor in fusion reactions. That is, the amount of yield we want should be greater than 1. That's the energy that's coming out is more than the energy we put in. Now, the challenge is, of course, to do it for a long enough time, and so as to allow a conventional setup of, let's say, water or steam or some gas to absorb this heat that's coming out of the reaction and run a turbine and eventually generate electricity. So that's the conventional setup. The fusion reaction would just be the furnace, if you like, of a power plant. Yeah. So can this be done on Earth? Well, maybe. We'd have to shrink all of this into an extremely small, manageable size, because in the case of stars, they're huge. We can't afford to have something that huge which compresses everything by its gravity and produces temperatures and pressures that are required for fusion. We'd have to do this in a very innovative way. But has this been done? Yes, it has been done. Marvel Comics has proven that you can do this. You have Mr. Stark here, who tried to do it in an extremely small reactor, which he called the arc reactor. And you have Dr. Otto Octavius here, who tried to do it and fend off Spider-Man. He failed, though. But anyway, we're going to try and succeed at this. So the conclusion is this is possible. Let's see how. Well, so if we follow the same thought process I told you earlier, extreme pressures to kickstart the fusion reaction, to overcome the nuclear forces, and then maintain those conditions for a long time to then eventually keep the reaction running. And of course, generate enough power than we put in, more power than we put in. Now, how can we do this? We need to confine this in a small area. Like I said, we can't use a star, we can't use a huge, the universe. We have to have a small area. And to do that, we need materials that would isolate this reaction from the rest of humankind. Now, we need something that can bear those temperatures, because we don't have anything right now that can bear such extremely high temperatures. Well, what we can use is something that doesn't have any contact with plasma, with the gas that's burning inside, and that's so violent. So magnetic fields work on magnetizable objects. They can manipulate and move objects that can be magnetized. So plasma, this is something I didn't tell you earlier. Stars consist of plasmas, and plasmas are the fourth state of matter, which are basically gases that are ionized. So the atoms of the gases are ripped apart, and you have electrons and ions that can be manipulated as electrically charged, moving groups of atoms. And so you can apply magnetic fields and electric fields to manipulate and move these collections of charges and electrons. And so magnetic fields then play an important role to help us isolate this whole burning plasma or the reaction. Okay, yeah, and the way to do that is, well, you have 3 images here at the bottom that show 3 possible scenarios. The first one here on the left is what we call as a mirror device. You have a sort of a cylindrical tube with magnets at the 2 ends, and these magnets here, these circular magnets, generate magnetic field lines that are parallel to the axis of the tube. And then what's done is you pump gas into this, hydrogen gas, you ionize it, and you split the gas into ions and electrons. And then you heat it up with lasers and beams, and then you wait for fusion to happen. But the problem with this type of devices is that the magnetic field lines are open at the ends, and so there's a lot of loss, a lot of particles that are inside, a lot of fuel particles like hydrogen and deuterium. They flow out, and we are not able to maintain this temperature hot enough for a long enough time. And like I said in the beginning, we need this to last for at least a few seconds if we need to make good use of this heat. At least a few seconds, hopefully more. So the trick would be to then maybe take these field lines and sort of close them onto each other. Like that's what's done here. You have a cylinder which is turned and made into the form of a torus, and you have field lines there that close onto each other, which means they never go and strike any surface. They are forever running into infinite circles. And so you have this, which is one scenario here where you can generate the fusion reaction inside a magnetized torus. And this is the third scenario where you have a small particle of tritium and deuterium, that is the isotopes you need for fusion, and it is held at the center of a device that is surrounded by extremely powerful lasers. Now, this is true, this is not science fiction. And this exists you have such facilities in France, in the United States, and I believe they're building one now in Europe, in the Netherlands. It's under construction. And this is basically a facility where you micro-explode little fuel quantities. So, for example, you have a fuel pellet of the size of 3 or 4 millimeters, which is placed very accurately at the center here, and then it's subjected to extremely powerful lasers, and these lasers then compress the fuel pellet and create temperatures and pressures sufficient to ignite this into fusion. Now this has another ulterior motive. This method of doing fusion is used also to study micro hydrogen bomb explosions. And so we're not going to look at that today. We will look at this one here because this seems to have generated a lot of success across the world in running fusion reactions for a few seconds and for up to a few minutes sometimes. So we're going to confine ourselves to this. And this is called magnetically confined fusion, because you use magnetic fields to confine it. Whereas in this case, you use lasers, you don't use magnetic fields. So both these are magnetically confined fusion devices. The toroidal device is the most successful one. Well, moving forward. So you have several configurations of magnetically confined torus reactors. Now, this is what you saw earlier, a simple circular torus, where you have these little gray toroidal field coils, which generate field lines that are running in circles inside them. And you also then have other vertical magnets, which are not shown here, but maybe you could see them here at the center. Now, these generate vertical field lines. And so you have vertical field lines that run through the center here, these black little lines. And so that causes the field lines inside the torus to be twisted to a certain extent. Maybe you can notice them here. They are pitching all downwards. They're not running as straight lines. They're pitching. And that's just a detail. It's not important, but it's important for the reactor stability. So this is one configuration. This is called the Tokamak. And it's an abbreviation of Russian words. I don't think I should tell you the words because I don't know them myself. But it basically means a toroidal bottle with magnetically confined plasma. Okay, that's what it translates to. And then you have further configurations of a torus, which are even more complex. On the right-hand side here, you have what is called as the stellarator version. Stellar, which comes from stars. And the stellarator is basically an optimized version of this device, which consists of, as you can see here, the yellow and the red lines are basically magnetic field coils. What you see here is gray coils, which are simple circular coils. Here they are extremely complicated. They are three-dimensional structures. Each coil looks something like this in the plane, but if you look at it in 3 dimensions, it's twisted and it looks like a snake. And this is done because these devices are prone to certain instabilities with the gas inside the plasma. It begins to move and bounce around and can be sometimes very violent and damage the reactors. So these devices have come up now as a sort of a solution to the problems that we saw in these devices. But they're extremely complicated to build. They take very long time to optimize because you need field lines that are to the nanometer precise in their position and orientation. You can't go wrong. And they're extremely expensive. But this exists. It's not a conceptual design. This has been, so this white casing you see here with lots of holes is what's covering this device. It's the vacuum vessel, because everything is maintained under vacuum inside for the magnets to be kept cool enough. And all these little holes are ports for supplying heat and diagnostics and checking the temperature. Basically, whatever you want to do with the plasma, you do it through these holes here that you see. And this exists in the north of Germany. This is called Wendelstein 7X, this stellarator, and it's been running since last year. So it's not completely impossible to build a fusion reactor. Well, now I come to so this configuration here is what is being tested now in the south of France. This is a little place in the south of France where a lot of mushrooms grow, and they have beautiful hills. It's very close to the Alps, actually. It's called Cadarache, and there you have a site that has been dedicated to building the world's largest fusion reactor. This is what the reactor would look like. And if you want an idea for size, I don't know if you can see it, but there's a little man here standing. That's the size it would assume. It's about the size of an Airbus, the volume, if you like. So it's really big. And this is where the plasma would be sitting inside. These are the vertical field coils. These are the toroidal field coils. They're no longer circular. They're in the form of a D shape. And you have lots of ports on the side here. This is a port for supplying heat and doing diagnostics, for checking temperature, measurements, properties of the plasma. And this is all enclosed in a vacuum vessel, which is this gray-colored vessel here. And basically for the success of fusion, you have a figure of merit, which what we call as the triple product. It is the density of the gas inside this chamber multiplied by the confinement time, I will tell you what it is, and the temperature of the plasma. And that's shown here on this graph. Basically, this product, it's called the triple product. The density times time and temperature should be greater than 5 into 10 to the power 21, which is a large number. And so the larger this is, the more successful or the more likely it is to have fusion, which is economically viable. Basically, the confinement time is the time that the plasma contains energy and doesn't lose it to the surrounding. Okay, that's what confinement time is. So this product is used as a figure of merit to decide whether the reactor that you have designed is good enough for doing fusion. Now, what we see on this graph here is different reactors that have been built in the world. This is the temperature at the bottom. It's on a log scale. And here on the log scale, you have the triple product, which is going up to 100 times 10 to the power 20. We need to be at 5 10 to the power 21 to have a decent reactor, which means somewhere around here and above. Now, all the reactors that we have built so far are below this 10 mark. The ones we are building now, that's ITER, that's the reactor there, this one, is planned to be here, which is slightly above this 10 mark. And over here you have the timeline. So this is what we've done so far, and this is where we plan to go. And the timeline for this one is a bit vague right now. It's probably expected to be online in 2024. We expect to have the first plasma started inside the reactor in 2023, and then go on to do some tests, and then eventually start fusion reactions in 24. So this is where we are headed. And this trend, they say, is like similar to the trend of microchip processors. The way the microchip processors advance with time, you have a log scale, and you have an increase that is similar to the improvement in fusion plants. I don't know if someone's here from electronics, maybe they could corroborate this, but anyway. And then just to give you a bit more information about this reactor, this is in participation with different countries. So you have the European Union here, which is doing the bulk of contributions to this reactor, about 45%, because the European Union is large and has several countries that are part of it. And then you have the United States and Japan, Russia, China, India, and South Korea. And new additions are Iran, I think, and Australia that have joined this consortium. And it is the world's biggest scientific project at the moment, much bigger than CERN, which is in Switzerland. And so everyone wants to be a part of it. So we shall talk more about this type of reactors. Well, it's quite nice, actually. So to give you an idea of how the Tokamak works, this is what the interior of the reactor looks like. This is a snapshot of the JET reactor, the Joint European Torus, which exists in the United Kingdom. And this is a camera view of the interior. You have the torus, and you have tiles on the walls that protect these walls from the extreme heat that is coming onto these walls. And you have tiles at the bottom that are slightly different. They're able to accept much larger heat fluxes. Now, the plasma actually sits on these bottom tiles, and that's where it touches the walls. It doesn't touch the walls anywhere else. It touches only here. And so these tiles are very specially prepared so they can absorb very large amounts of heat fluxes and particle fluxes. So what's done is the plasma inside this chamber is, like, as you can see here, it's shown separately in a sketch. You have particles that run around the field lines, and electrically charged particles gyrate around magnetic field lines. So these gyrate, and then they're given sufficient velocity to move in a toroidal direction, to circulate along the field lines by various heating methods. So what we do is we use a combination of ohmic heating. So ohmic heating is nothing but running current by induction. You are all familiar with induction. When you move a metallic object in the presence of a magnetic field, you end up creating eddy currents and charges that move inside these metallic objects. So the plasma that exists inside this reactor is like a metallic object because it has free ions and electrons, so it can readily carry current. It's a good conductor of electricity. So what's done is you have a central solenoid, which is here inside this, which begins to change its magnetic field with time, and so as a result you have a current generated, induced inside the plasma. And this is what is used in the beginning to ionize the gas, and then eventually heat the plasma a little bit. And then, because you cannot heat this to a very large extent with this induction heating, you use neutral beams which pump neutrons into the gas, and they heat the gas through collisions. And then you also have radio frequency heating, where you use an assortment of radio waves, because based on the density of the gas that is inside, they are able to absorb certain wavelengths or certain frequencies of the radio waves that are coming onto them, and they get heated up, and these particles attain higher energy, and then the temperature of the plasma begins to rise. So this is what we do to heat the plasma initially, and then also maintain its heat. We mostly use radio waves. Well, now, what happens is when you have such high temperatures inside the plasma, it needs to dissipate all this energy at some point and to some part of the reactor. Now here what you see is a cross-section of basically of the plasma, a cut of the torus, and we see that it has a sort of an onion skin structure where you have different concentric circles. Basically, this is nothing but different magnetic field surfaces. You have magnetic field lines all along the torus, and you have different surfaces that have different magnetic field strength basically inside it. Now, what happens is if you check the temperature at the core, which is here in the middle of the device, and all the way till the edge, the temperature varies from about 5,000 electron volts to 0 at the edge. Now this translates to about 56 million Kelvin at the center to room temperature at the edge, basically. And, well, close to room temperature. It never goes to 0. And the density is also follows the same trend. You have extremely high densities in the middle here, 10 to the power 20 per meter cubed, and at the edge you have nearly nothing. Now, this just goes to show how much of material and temperature you are trapping in the center, and how much of it needs to come out. And so it all needs to come out at some point. It's going to come out at the edge, where the plasma is facing the walls of the reactor. And we need to be prepared for this. Now, the plasma faces the walls all around, but it doesn't touch them. It touches them only here at the bottom. Sometimes at the top also, but that depends from reactor to reactor. Now here at the bottom, as you see these red lines, they touch the walls. And this part here at the bottom is called the diverter, and this is where the plasma sits. It touches, and it dissipates heat, it dissipates particles, all the waste helium particles that come out of the fusion reactions, they go down there, and they are pumped, and all these surfaces are actively cooled by coolants that flow at very high pressures and very high velocities. Now, because there is so much energy trapped in the center of the plasma, this eventually dissipates to the exteriors where the plasma is rather cold, and we're going to see how this happens and what happens when this happens. Okay. Well, now for example, in the ITER case, you have a gain factor. What I told you earlier was the yield or the gain factor, which is the amount of energy you put in and the amount of energy you get out. Well, ITER has a target of 10, which is the minimum target for ITER. And we plan to, of course, go beyond 10, but this is the minimum target. So when you have a target of 10, the amount of fusion power that's generated in this reactor is about 500 megawatts of heat. And of that 500 megawatts, about 20-25% comes from the alpha particles, which is the helium coming out of the reactor. And that's about 100 megawatts. Now, all of this, like I said earlier, it comes out somewhere and at some point, and it comes out here at the bottom, at the diverter. And so we need to be prepared to receive this heat and make sure that our reactor doesn't get burnt and melted. Now, it's a lot of heat because if you think about it, I've given you a graph here. This is just to give you an example. We've all seen an arc welding torch that's used to weld. Now, if you look at the temperature or the heat flux of this torch, and as a function of distance from the torch, and if you are at a distance of about 4 millimeters, you're already receiving 10 megawatts per meter squared. If you're at a distance of about, say, 2 millimeters, you're receiving about 40 megawatts per meter squared. This is just to give you an idea. If you look at a torch, imagine 2 millimeters away from that torch. This is the amount of heat that's coming onto your hands if you put it there, okay? Of course, don't do that. So now this heat is what is the limit for ITER. 40 megawatts per meter square is the limit with which we've been able to design these plates at the bottom there. And they cannot accept more heat. They will burn, they will melt, they will get destroyed. So now what we need to do is some of the, for example, here there's an image. I don't know if it's very clear. It's of a melted tile, and this is what happens when heat goes beyond bearing capacity of the material. So you can just think of a giant torch inside ITER on your tiles. And basically that's the problem we have right now, and we need to try and find a way to reduce this heat that's coming out or increase our material bearing capacity that can accept this heat. And that's exactly what's done. For example, what the engineers try to do here is that they try to increase the surface area of these tiles so that they could accept more heat, because the flux would then get reduced because it's heat per unit area. So now to reduce it, what they did is they increased the inclination of the tiles, so the tiles got inclined and bigger, and as a result, the field lines were not hitting them vertically, but they were hitting them at an angle, and so you had larger surface area to dissipate the heat. Now, doing all that, we've come down to we've come down by a large factor to about 600 megawatts per meter squared. We need to come down even further, yeah? And there's another problem. In ITER, or in any magnetically confined device, all the heat comes out through a very, this part here is a blow up of this little piece here. So all the heat coming out of the reactor flows through a very narrow channel here onto the target plates. And this channel is extremely narrow. It's about a few millimeters. So that, again, reduces the surface area we have available to absorb this heat. If this area was large, then we would be able to use very large tiles and absorb all that heat. But unfortunately, all that heat, 100 megawatts, is going to come out into just a surface that's as thick as 1 to 10 millimeters. Okay, so that makes things even more difficult for us. Well, another effect in the edge is that apart from these large heat loads, these are images of two reactors. One is the Torsupra in France and Mast in England. We have seen in the edge, we've seen these filament-like structures that form, which carry very large amounts of heat compared to the rest of the plasma around them, and very large amounts of particles. And so these structures are quite dangerous for the diverters, as I mentioned earlier, which are already receiving very large amounts of heat. And so what I personally do is I study these structures in the reactors to see how they behave and what is the physics behind their generation and their dissipation, and to eventually come up with a way to maybe understand them better and avoid them if possible, or manage them. So how could we study the edge then? So basically, to study the edge region of the plasma, which has all these violent phenomena, we can use computer modeling. Now, to make a model, it depends on what you're interested in, whether you're interested in microscopic quantities or macroscopic quantities. Now, we're interested in a bit of both. And so depending on the detail you require, you would have a consequent description of that detail with a physical equation, and then eventually you convert it to a numerical form. Now, if you study at the individual particle level, then you are at a very microscopic level. You have to study each of the particles present in the reactor, and as you know, you have 10 to the power 21 of that order particles per meter cubed. So it makes it very difficult to study at such detail and to model them. Although it is being done, but it's numerically very expensive. You need to run simulations that last months. For example, the last simulation that was presented at a conference using these methods for fusion it was run for about 1.5 months, the simulation. And it was run for a very small part of the reactor. So it's prohibitive in terms of modeling and numerical costs. Well, another method is to use kinetic theory, where you look at the evolution of the distribution function of these particles. So you consider your plasma to be consisting of different species, for example, ions and electrons, just an example. And you assume that the distribution function is known in some way. Yeah, you can assume a Maxwellian distribution, for example, for one of the particles. And then you study the evolution of the distribution function. But again, this is also prohibitive because of the number of degrees of freedom you have in the system and the amount of computing resources you require for that. And the final way, which is a further approximated version of this, is a fluid scheme where you study the gas or the plasma as a fluid. And this, of course, is done very widely. It's still quite expensive. But depending on the resolution you use and the amount of detail you want, you can make compromises and then study something to some amount of efficacy. Okay? So what I'm going to talk about is this bottom one here, basically a fluid description of plasma. And so basically how to do it from first principles, what we do is we start with the Boltzmann equation, which is the evolution, the time evolution of the distribution function f of a species S. Okay? This changes with time, so you have the material derivative here applied onto the distribution function, which basically tells you how the distribution function evolves in time, and you have a collisional term here which tells you the change in the distribution function due to collisions. And this is basically the Boltzmann equation. What we do in fluid modeling is we assume that this is 0, that the change of the distribution function due to collisions is negligible. And so we say it's 0, and then expanding the material derivative, you have simple time evolution of the function and convective terms, which is shown as a Poisson bracket. Sorry, S prime is another species of gas collisions and exchange with another species, and so the interactions between the two causing change in distribution function. Okay. I know you're a mathematician, so don't judge the math. I am a physicist. All right, so what we do is we're here now, and we assume that the collisions have no effect. And so this form of the Boltzmann equation, which is written here in its expanded form, is called the Vlasov equation. So basically you have a time evolution term, you have a convective term, and then you have a force term here, where F is basically all the forces acting on the plasma particles. And we ignore contribution of collisions. So now this is where we would start to arrive at a fluid model. From this place, what we do is we then, so in terms of, for the case of plasmas, the force is nothing but the Lorentz force. I think you're familiar with Lorentz force from basic physics. And that would go in here, okay? Now, how to arrive at a fluid model from this? Here, you're still talking about the distribution function. Well, to arrive at a fluid model, what we do is we project this Vlasov equation onto a basis which consists of velocities of different orders. So you have 0th order of velocity, 1st order, 2nd order, and then we arrive at a set of equations. Before we do that, I'll just summarize some quantities. Now, the integration of this distribution function over the entire velocity domain is the density of the particles. The first order moment, that is if you take v raised to 1, which is v, multiplied by the distribution function integrated, is the velocity of the fluid. And then the second order gives us pressure, The third order gives us energy. So as you go up in order, you get higher quantities. So this is just to keep at the back of your mind, okay? So when we project the Vlasov equation shown here, when I say project, I mean you just multiply this basis vector with this equation. So you would have v raised to 0 times this integrated, v raised to 1 times this integrated, and so on till some k. You get, for example, when you take v raised to 0 times the Vlasov equation integrated over the entire domain, you have the continuity equation. This is the 0th order moment, as we call it, because you're sort of doing a moment multiplication. You have velocity times something. The first order gives us the momentum equation, momentum balance, or the Navier-Stokes, as some of you call it in fluid mechanics. And then the second order gives us the energy balance equation. Now these seem complicated. We won't use these equations, but this is just to give you an idea of how you come to a fluid approximation from for a gas which consists of different species that have different distribution functions. If you, under certain conditions, you can approximate it to behave like a fluid and to have collective behavior, and so you do this and you end up with fluid equations. Now, at some point you'd have to stop, because you can go on taking several moments and you'd get different equations, but then we also wouldn't know how to interpret these equations, because you have already continuity, you have momentum, you have energy, then you would have something else, and so physically it becomes difficult to treat these quantities and to make sense of them, and then to eventually use that information to understand what's happening in the plasma. So what we do is we can either truncate at this point and this point, or this point, and in each of these equations, if you've noticed, in the 0th order equation, you always have a first order term, that is v raised to 1. Here you have a v raised to 2 term. Here you have a v raised to 3 term. So you always have a higher order term in a lower order moment. So that's a problem in this fluid formulation, and you need to stop at some point and just make an approximation for this high order term that you see here or here, and say that, okay, I'm going to assume that the velocity behaves like this. I'm going to assume that the momentum behaves like this. I'm going to assume that the heat is bounded by these conditions. And you stop your moments, and you just take the equations you have that you're satisfied with, and you go on. Basically, you can go on to infinity for v0, v1, v2 until v raised to infinity. And if you are able to solve all those equations, you are exactly equivalent to a kinetic description. But since we can't do it, it's too tedious. It's impossible, basically. So we stop at some point and we make some assumptions, as physicists are known to do, and we treat the problem at hand. So now, what we do in plasma physics very often is we stop at this or this order, at the energy order or at the momentum order. So yeah, basically we can stop talking about the fluid description now, and we can actually see how we use the fluid description. Now, what I use is, it's called the Tokamak 3x model. It's a fluid model. It consists of the density evolution here. N is the density. You have a source term, you have a diffusion term, you have an advection term. Excuse me. Then we model the parallel momentum, the evolution of the parallel momentum, and you have a third equation, which is the balance of charge, and you have a fourth equation, which is the Ohm's law. So basically, we have four unknowns, and you have four equations: density, parallel momentum, the electrostatic potential, and the current. Now, this equation here is basically for the electrostatic potential, but you don't see it here because W is related to the electrostatic potential via this. Okay, so you have 5 equations, but we basically have 4 unknowns. So we are well resolved, and this is what we use in the Tokamak 3x model to solve these 4 unknowns, and then track their evolution in time and at every local point in our domain. Also, the model is very complicated. I won't go into details of each and every equation, how we derive them, because that would take a long time. But this is just to give you an idea of what are the quantities involved and how we do it. Now, there are some underlying hypotheses. Like I told you earlier, under certain conditions, we can use the fluid model. So basically, these are the conditions, that the temperature is low at the edge, and as a result, the gas is not so, each of the species are not so independent of each other. You have collective behavior, which is more dominant than individual microscopic behavior. The plasma is quasi-neutral, which means that it's almost neutral. There is no net charge in the plasma. And the electrons move much faster than the ions, so the motion in the plasma is basically due to one species, which is the electrons. The ions are much more heavier, about 2,000 times heavier than the electrons, and we consider that the temperature is equal for all species, okay? So these are some of the assumptions we make to be able to apply a fluid description onto a non-fluid regime, actually. And so, what we then do is we can then use this mathematical model to study different parts of the torus. This is the torus here, and these red and blue lines are basically field lines that twist across the torus. And with the Tokamak model, we can use it to study the filamentary structures we saw earlier in camera snapshots of the two reactors. Now, how to do that, I will explain to you. But with this slide, I wanted to emphasize just one point, that is, we are able to study a diversity of geometries and physics inside the reactor. Now, if you look here, this is the complete three-dimensional torus geometry. But we can also study just a small section, which is like a parallelepiped going along a field line. And in doing so, what we do is we use less computational resources, because you're using less space, a lower mesh. You don't need as many points as you would need here, for example. You would need very few points. And you can get your results faster. And sometimes you're just looking at microscopic detail. You're not looking at the whole reactor. You just want to know what happens in one part. And so this is what we can do with the Tokamak reactor, the Tokamak model. And it's also quite versatile in terms of the kinds of geometries it treats. Now here I haven't shown you too many geometries. It's just the toroidal geometry. But we can apply it to more complicated geometries, okay? Now, filamentary structures usually are confined to a field line. They stick to a field line and they move towards the walls as they are confined to the field line. So this type of geometry is quite ideal for studying filaments. Basically, you confine a small section around a field line and you study it with the model, and you see what happens to a structure that might appear in that domain. So what we do is we construct a parallelepiped with parallel field lines that are parallel to the long edge of the domain. We then assume a background plasma. We generate it with the model, and we then seed, or we impose a smaller, a large density, small structure. That's here. You can see it as a spot. Now, what you're looking at here is basically this plane here. You're not looking at the field line. You're looking at the cross section of the field line. So there is a high density structure here along a field line, and then with time, this structure begins to move and convect towards the wall. Basically, it's like a little drop that's moving across water, through the depth of water, okay? So you have high density here, and you have low density here. As you know, earlier I showed you the density is higher inside the reactor in the core. So what happens here is basically an interchange mechanism. It's when you have small fluctuations, I've demonstrated the interchange mechanism. Basically, how this moves is you have the generation of an electric field that is vertical here. It's not seen here because here you can see only the density. But here, for example, this is the density and this is the electric field. As little perturbations arise, this electric field grows and it begins to convect the density towards the wall. And this convecting velocity is called the E cross B velocity, which is here at the bottom. So we understand the basic mechanism of how these structures move in the plasma, but we don't know what can change their motion or what can affect their motion and what can affect their size and the amount of particles and heat they carry, these structures. So that's what we're trying to understand. So this is a very simple model, simple simulation. What we then do is Here I show you how these simulations are tracked, how these filaments are tracked. So here you see another filament that is traveling. This is the density of the filament as it begins to deform, the cross-section of the density of the filament. At the bottom, you see the electric field associated with this. It's bipolar. You have a positive and a negative color here that shows the positive and negative electric potential. And as this moves, this begins to grow, and the electric field also begins to grow because the distance between the two poles is increasing. What we do is we track these structures using a tracking mechanism or a tracking algorithm, which identifies certain densities and then follows these structures as they move. And that's shown here. I don't think it's very clear, but anyway, what we do is we filter the structure, and we only look at the high density portion of that structure, and we follow it, and we look at what happens to it. Here what you're looking at is the structure along a field line. It is undeformed, it is moving along a field line, and these structures are known to move entirely along field lines. They don't break very easily unless they're subjected to certain conditions. So this is an example of how we studied an experiment and validated what we saw in the experiment with what we saw with the code. And now the Tokamak 3x code was used in a multi-code benchmarking project where we compared the code's output with 3 other codes. Here you have the storm code. The top series of images was generated by the storm code. The second one was by the GBS, which is a Swiss code. This is an American English code. Tokamak, which is the code I use, which is a French code. And this is a 2-dimensional code. These 3 are 3-dimensional. So anyway, this was an exercise to check what we are generating in the simulations, whether it's close to reality of what is seen in experiments. So in the experiment on the masked English Tokamak, these structures were observed. One of the structures was isolated, and its properties were studied very rigorously by the experimentalists at the reactor there. And then they told us, this is what we know about the filament. Can you simulate it with your codes? So we tried to simulate it. Each one of us, each of these teams, then went on to simulate these filaments and to see whether they behave the same way as what is seen in the experiments. And what we noticed is that, for example, on this graph here, you can see the radial motion. So on the left axis, you have the radial motion, which is r in meters. And on the x-axis, you have the time. So what we did is we tracked the motion of the center of these filaments and with time. And so we saw that the red line is the experimental line here. We saw that most of the codes followed the initial part of the motion, but then later on they were unable to simulate the long time period behavior of the filament. There's one model which couldn't simulate it, which is, well, it was far off, which is the 2-dimensional model. And this actually opened up the whole debate on to whether 2-dimensional models are good at predicting 3-dimensional phenomena. And this is something that we still don't know very well. On this here you see, again, so these are 2 different filaments. This is 1 and this is 2. One of the filaments, it went off for the second filament. They were all pretty much close by and close to the experimental curve. The experimental curve is the gray area here, the gray. This is the error bars of the experimental curve. So this is just to give you an example of what you can do with the code and what I did with it. And there's a publication now. This is out, and it's been cited quite well. And it also helps us to understand differences between various models that exist out there and what you can do with your model. This is another test that we ran. What we're showing here is the way the velocity of these filamentary structures changes with the size of the filament. Now, a lot of people came up with theories about 20 years ago about how the velocity of the filament changes with its own size. And so here what we did was we simulated various size filaments and we observed their velocity. And so here you have the size of the filament on the horizontal axis. On the vertical axis, you have the velocity, which has been normalized. So we observe that for low sizes, the filament velocities usually increase, and then as they become bigger and bigger, their velocities begin to reduce. This is something that's very universal and was observed across devices and across filaments, and this is something that is recovered by the code, and which is a good thing actually, because we're close to what's seen in reality, in experiments. The different color lines are basically for different inclination of field lines. We try to change the field line inclinations to see if it changes anything. It doesn't. In this graphic, you're looking at, again, the same, the velocity variation with size of the filament. But here what we did is we changed the background plasma properties. We increased the resistivity, and we wanted to see if that has any effect on the motion of the filament, and that indeed does have effect. If you increase the resistivity, the filaments are much faster, even if their size is increased. For example, these curves here that are tending to go up are the curves for larger resistivity of the background plasma, whereas these curves here, the black one and the purple one, is for low resistive plasmas. And so this is actually a very interesting observation, because we didn't know that this would happen, and this is what is also now being observed in reactors. And so this is the last slide. This is what we are doing further to study these filamentary structures at the edge. We are looking at the effect of shear. Now, in fluid, shear is basically a change in velocity with distance, or the complete change of direction of velocity with distance. But in plasma physics, shear is nothing but the change of the orientation of the magnetic field lines, and that changes also the direction of flow in the plasma. So what we're trying to do is, with the model, we're trying to change the orientation of the field lines and see whether that affects the motion of the filaments towards the walls. Then we're also doing a multicode validation, just like we did earlier for filaments. We're doing a multicode validation for a fully turbulent torus geometry, which is more expensive to run, with fully turbulent plasmas, and we are observing filamentary structures that spontaneously arise in this turbulent plasma. Another study is on the effect of field line shear. Now, we did a little bit of investigation earlier, but that is not the end, because shear exists in different forms. I wish I had more time to explain to you how shear works inside the magnetically confined devices. But as you know, there are some devices that are extremely complicated in their configurations, and as a result, the orientation of field lines can be very complicated, which gives rise to shear. So this is another study that we're doing. And of course, blobs around X point. So the filament is also called as blob, because in its two-dimensional description, it looks like a little blob. But in its three-dimensional description, it's a filament. So we are looking at how they behave around the X point. And the X point is nothing but this region here, because this region is very tricky and difficult to understand, because here you have field lines that intersect, which should actually not happen, so we don't know what really happens there. So we are trying to study this region and filaments and how they behave around that region. So, well, thank you.
Bueno, muchas gracias, William. Ahora, si alguien tiene alguna pregunta que hacer. Bueno, vale.
Thank you. Can you go to the 7th slide?
Yeah. Tell me to stop. Okay.
It's in the 7th, I
Oh,
think.
sorry. This one?
There, yeah.
Okay.
Okay, in the third way, you say that this could happen. You said that it was like a solid material, right?
Yeah.
Right?
Yeah.
And how can that solid material be held with something that will fuse it gets too high? I don't understand that.
How can it be cold?
No, like in the other two,
Yeah.
what we are trying to do here is to make all the material be contained with magnetic fields, right?
Yes. Yeah.
But it doesn't happen in the third one.
No, so in the third one, you don't use magnetic fields at all. It's just lasers that strike very precisely a small target, which contains the fuel deuterium and tritium, and with shock waves, they compress or they implode the target, that is the fuel, and that it gets confined, what is called as inertially. By its own inertia, it gets confined because you have lasers that are so precisely positioned all around this target, and they impinge at the same time. So it's basically it's something very difficult to do, but they do it. And
But my question is,
yeah,
how can you hold the target?
yeah,
Because the
okay.
problem with the other
Good
two
question.
is that you cannot touch the.
So what they do is, it's not a very convincing method, which is why I don't study it. But what they do is, they use an arm to hold the target before the reaction starts. Once the lasers are initiated, the arm is retracted, and the fuel element remains in the middle of the chamber, just by virtue of the pressure, the laser pressure applied on it. It's a very tiny element. It's about 2 or 3 millimeters in size, and yeah, that's what happened. And this is one micro explosion, and then you need to bring another fuel element. So this can't go on for a long time. This has to be done intermittently. So
Okay,
I don't know if that answers your question.
Yeah, thank you.
¿Alguna otra pregunta? I wanted to ask you, when you compare the 4 algorithms, the
Yes.
2D and 3D ones,
Yes.
the French one seems to have a stronger result than the other 3.
Actually, just the opposite. The French one, which is the one I use, performed the worst on the first graph, and there's a reason for that. It's a good thing you asked me. Well, the French one is the black curve here at the bottom. The other two, the green and the blue one here, are these two codes, the Swiss and the American code. And this is the Danish code, which is 2-dimensional, completely off the mark. So what we were trying to do is trying to approach the red curve, or the gray area here, which is the error bar region of the red curve. Now, the other two approximated that curve really well with their codes, but the French code doesn't. And that's because if you look at the slopes are more or less the same over here in this part. But it's in the beginning that the French code is a bit slow. And this is because what we do is, in our code, we do not initialize an electric field associated with the blob ourselves. We don't punch in some numbers and say, okay, start. Because what that does is the electric field adds a spin to the structure, and it gives the structure more velocity. All these guys, they did that. They approximated the electric field associated with the filament from the experiments, and they fed that into their codes, and so they approached the experimental curve better. But we didn't do that. We allowed the electric field to self-evolve to be more consistent, because we didn't want to give any bias to the simulation, and which is why the simulation initially takes some time to generate the electric field, and then it begins to evolve. But otherwise, if you look at the global behavior, the slopes of the 3 curves are more or less the same in this case and in this case, for both the filaments, basically. So the French curve performed badly in that sense, but it was consistent, if I can say that. I don't know. Yeah.
Yeah, in one of the first slides, you presented a regular toroid.
Should I go to the slide?
Yeah, please. And what with twisted magnets. That I understand is kind of an improvement of the Tokamak.
Oh, sorry. This one?
Previous one, this one.
This
But
one?
yes.
Okay.
If the right one is an improvement of the Tokamak,
Yes.
then why are we building?
Why are we not doing that?
Yeah, why are we building a giant Tokamak instead?
All right, so good question. So this one, the Tokamak concept is something that's been tested by the whole world. Almost all countries except for Spain have Tokamak. Spain actually has a stellarator, but it's a very small experimental stellarator. And the stellarator, it's quite contradictory actually. The stellarator was the first fusion device to be built, but it was used as an experiment in the United States to try out something. And the Tokamak became widely popular because the Russians started using the Tokamak, and they had a lot of success with it. And then the whole world tried to replicate what they were doing, and as a result, everyone built Tokamaks, and people sort of forgot about the stellarator. But then what they realized is that these are prone to these, like I mentioned earlier, these instabilities, and these devices aren't. Now, the problem with stellarator is that we don't have as much information as we have for Tokamaks. And we already know enough about Tokamaks to sort of put in our money there and try and demonstrate that it works, and maybe use that to then build a much better stellarator. Physics are similar, but these are much more stable. So if we know how to run a Tokamak, we should be able to know how to run a stellarator. But now the first device, that is this one, the first large-scale device that is built in Germany, the Wendelstein, is going to give us that information that we didn't have about stellarators all these years. And maybe after that, we might build, I guess, countries would actually build stellarators instead of Tokamaks. You know, you always need someone to take the first step, and it's Germany, so. Thank you.
Hi.
Hi.
Hi, my question is, what is the largest value of the Q factor that we have ever achieved?
Well, if I can show you on the graph. Oh no, I don't have it here. Okay, well, the Q factor, the largest Q factor, it's not here, sorry. The largest Q factor achieved is 1, Q equals 1, which means you pump in as much energy as you're generating. And that's called break even. So you're doing the minimum possible. But the trick is not how large your Q is, the trick is for how long you can do it. Even if you do Q equals 1, if it doesn't last for more than a minute, then it's useless.
So the largest Q factor has been 1, but what is the largest confinement time that we have achieved?
The largest confinement time depends. It depends from device to device. We've run it for 30 seconds to 130 to 300 seconds. In Korea and Japan, I know that they've run it for longer time durations. With ITER, we plan to run it for 400 seconds at a Q of 30. At a Q of 10, that is the minimum Q. We have other scenarios with ITER where we will run it for Q equals 30 and 50. But that depends on how Q equals 10 goes. If that's fine, then we will run it for higher Qs.
Okay.
And yeah. So.
Thanks.
Bueno, si no hay más preguntas, otro aplauso a William.
Thank you.